Thanks everyone for listening in to my talk. I'd like to tell you about a simple system of lossy qubits that has multiple steady states with long-range coherence, which is rather unusual. This work was done with Professor Nigel Cooper at the University of Cambridge. So the setup we are considering is strongly interacting bosons in a 1D lattice, which are coupled to local reservoirs that inject particles at a given site P and remove particles from some other site Q. There are several reasons for studying this kind of setup. First, there is active experimental and theoretical interest, as a number of synthetic platforms are being developed where such systems can be engineered with a high degree of tunability. And a key motivation is to see new out-of-equilibrium phenomena that have no counterpart in Hamiltonian systems. These can also have potential technological applications if, for example, one can stabilize entanglement against dissipation. Further, the pump and loss in such systems can drive current through an interacting medium, and one can ask if they can be used as probes to extract information about the bulk, like a scanning tunneling microscope. So we model bosons in the hardcore limit. That is, the interactions are so strong that no two bosons can occupy the same site, which is why BI dagger squared is 0. We also assume the reservoirs are Markovian, that is, they relax to equilibrium much faster than the system dynamics, which is standard for quantum optics setups. Then the density matrix of the system evolves according to a master equation of this Lindblad form, where the operators L plus and L minus describe the pump and loss respectively. Some experimental prototypes of this model already exist. For instance, here, one has an array of nonlinear resonators in a superconducting circuit. The nonlinearity is strong, so each resonator effectively behaves like a qubit, and capacitive coupling between neighboring resonators gives the tunneling. One of the resonators is attached to a reservoir that is designed to inject photons into the resonator provided it is empty. Using such a scheme, a Mott insulator of hardcore photons was prepared in the experiment. Theoretically, our model has been studied where the pump and loss are at opposite ends, in which case the dynamics reduce to free fermions, and one finds a unique steady state with short-range correlations. In contrast, we study pump and loss at the center and find very different results. Namely, the system does not reduce to free fermions, there are multiple degenerate steady states, and they have long-range coherence in the form of entangled particle-hole pairs. I will address each of these points in the following. First, the Fermion description. Some of you may know that the Hamiltonian we have written down can be mapped onto free fermions using this Jordan-Wigner transformation. However, the dissipation becomes non-local in the fermion operators. For example, L plus not only depends on F0 dagger, but on all the fermions to the left of the center site. That is, it couples fermions at different sites, mediating interactions, so the physics is very different from free fermions. Nonetheless, the fermion picture will be useful. In particular, the Hamiltonian can be diagonalized in terms of these even and odd fermionic modes, which are just lattice analogs of the particle in a box wave functions. Now, the multiple steady states arise from a symmetry, C. We call it hidden because it doesn't correspond to a simple spatial transformation. But it can be expressed simply in terms of the total occupations of the even and odd energy modes, so it commutes with the Hamiltonian. Further, using the fermion to boson mapping, one can show that it depends on the bosons at the center site only through the parity. So C squared does not act on the center site and commutes with the dissipators, as well as with the Hamiltonian. The result is that C squared is conserved, and the full dynamics decouple into its eigenspaces, giving rise to multiple steady states in the different symmetry sectors. The physical meaning of the symmetry becomes clearer if one rewrites C in this form, where the operators ak plus minus are linear combinations of fk and f minus k. What they do is create entangled particle-hole pairs at sites k and minus k. Note there are two types of Bell pairs, depending on the sign, and creating both types of pairs just fills up the two sites, which are no longer entangled. So it is useful to assign a quantum number of plus minus 1 to these two types, which we call charge. Then for the states 1, 1 or 0, 0, the net charge is 0, and so is the entanglement. In other words, the magnitude of the net charge measures the entanglement. And the summation in C measures the total charge in the system, or the net entanglement between the left and right halves. Now, C is already in diagonal form, so the eigenvalues of C squared can be simply read off, and if one substitutes the possible values of nu and n naught into this expression, one finds there are L+1 distinct symmetry sectors labeled by this integer eta. Larger values of eta correspond to larger magnitudes of nu and hence to larger entanglement. So in summary, the hidden symmetry divides up the Hilbert space into L+1 sectors with varying degrees of entanglement. Now, it turns out that in each of these sectors, there is a unique steady state, which for equal pump and loss is simply given by the projector p eta, which is an equal mixture of all the pure states in that sector. When the pump and loss rates are not equal, these get rescaled by an effective chemical potential. So the steady state rho eta is like an infinite temperature state within the respective sector. Still, it can have high spatial entanglement because, as we saw in the last slide, all the states in a given sector can be highly entangled. For example, when eta equals L, its maximum value, one has bell pairs of the same charge at all positions. So the corresponding steady state is maximally entangled. The antidiagonal correlations here are indicative of the bell pairs at sites k and minus k. If one goes to less entangled sectors, these correlations fall off. In particular, the coherence between the two end sites, L and minus L, falls off monotonically in magnitude and is also relatively insensitive to the pump-loss ratio. Thus, it is a useful measurable quantity that can distinguish between the different steady states. Here you can see the single particle correlations in the different sectors for L equals 4. There is a clear contrast between the maximally entangled and the minimally entangled cases. One can also quantify the entanglement in these states by calculating something called the log negativity, which gives a bound on the number of distillable bell pairs between two halves of the system. As you can see, it rises monotonically from 0 for eta equals 0 to L for eta equals L. So there are these entangled steady states. However, the final state will generally be a linear combination of these, set by the initial weights in the different symmetry sectors. So the question is how to prepare the initial state in a given sector. Well, one strategy is to note that C is related to the even and odd mode occupations. So if one can start with a definite value of n odd, and then deplete all the even modes, then the system will be driven to the sector eta equals n odd. Turns out one can have a definite occupation of the odd modes by simply producing a symmetric Fock state, which is easy to do in experiments. Then n odd is just the total occupation to one side of the center. The next part of depleting only the even modes is more challenging. For this, one has to engineer loss of the Jordan-Wigner fermions at the center, which is non-local in the bosons. What this means is that when a boson is lost, the state has to gain a collective phase, which is the total parity of all sides to the left of the center. Although this is not straightforward, previous studies have shown how it can be implemented efficiently using ancilla cavities. Provided one can engineer this loss, the odd modes won't be affected as they vanish at the center, but the even modes will decay. So the system will be driven to the sector eta equals sum over nk. In essence, this process distills the negatively charged bell pairs and generates entanglement controlled by the initial occupations nk. For example, a fully filled lattice with nk equals 1 is driven to the maximally entangled sector eta equals L. So this is how one can prepare a given symmetry sector, which is the first step in producing a given steady state. A measurable signature of this process can be found by plotting the evolution of the end-to-end coherence. Here the different curves correspond to different initial occupations that are driven to unique symmetry sectors. The oscillations result from back and forth tunneling of the bell pairs. When the dynamics have stabilized, the system will have reached a given sector. Then one can switch from the fermion loss to the original boson pump and loss, which will drive the system to unique steady states rho eta. Note the entire preparation takes a few tens of tunneling time, which is typically much faster than residual dissipation and disorder in experiments. Finally, in this animation, you can see how a fully filled lattice evolves to a maximally entangled steady state. This is the part with fermion loss, where bell pairs are being formed, and this is the boson pump and loss. So to conclude, I have told you about a lossy quantum system that has multiple highly entangled steady states, and the steady states arise from a symmetry that stabilizes bell pairs over long distances, and one can also show that it applies to a broad class of two-level systems. Finally, we find other surprising phenomena in generic pump loss geometries, for which I refer you to this paper in arXiv. So that's all, and thank you for your attention.